Okay, I guess we're going to get started. Hi everyone, thanks for coming to today's colloquium, which is hosted by the physics graduate students. So every year the committee gets to pick a few professors whose work we're really excited to hear about. And today we've invited Professor Jim Crutchfield to talk to us about his work in chaos, complexity, and computational mechanics. Professor Crutchfield graduated summa cum laude from UC Santa Cruz with a degree in physics and mathematics, and also earned his PhD there only 4 years later. Since then, he's been a research professor at the Santa Fe Institute, where he ran the Network Dynamics program and also served as co-founder, scientific director, and president of the Art and Science Laboratory. He is currently professor of physics at the University of California, Davis, where he serves as director of the Complexity Science Institute, overseeing transdisciplinary projects spanning topics such as the structure and dynamics of networks, physics of information, and biological computation. So without further ado, let's welcome Professor Crutchfield so we can finally find out what demonology is.
Great. Thank you, Emily. I turned it on, but I don't see a green and or red light, so I'll assume, unless I hear complaints from the staff, that the recording is working fine. Oh, well, thank you all for coming. I very much appreciate taking the time off this afternoon to come talk about demons. So the conceit today, and this is a little bit, I don't know, maybe as one gets older, one feels like it's time to go back and read some of the original literature. So I've been going back through, Clausius and Boltzmann and Poincaré, Maxwell, the Ehrenfests, and I noticed this kind of curious thing, and also reading a little bit about Darwin, that these very strange appeals and these otherwise scientific works to this odd notion of intelligence. I've mostly been a physicist, and I think I've mostly worked on inanimate systems. So why would Maxwell, in trying to explain to me some of the subtleties of thermodynamics, namely the second law, make an appeal to an intelligent being? It's just sloppy thinking. Well, it just got me to thinking about what is intelligence in the sort of natural world? What does it mean that a piece of the inanimate world would somehow take itself up and act with some intention and agency? And are these notions completely out of the bound for physics? I don't know, sort of curious. And my readings kind of showed that there was actually this whole set of demons that people have been talking about, these sort of intelligent agents, going all the way back to Laplace and his thinking about the origins of randomness in the physical world, to Henri Poincaré, the French mathematician that discovered deterministic chaos, to Maxwell and his demon, and even, of course, to Darwin, Maxwell's contemporary. Why are they talking about intelligence? Maybe actually Charles Darwin is the only one who has an excuse here, but the others, we have a gambler, a mechanician, and E&M, and a little bit of thermo. Why demons? So the conceit, I of course have some technical things I want to tell you about, but I want to think a little bit about this context of sort of intelligence and agency, but in physical systems. And there's some way we can think about what these concepts might mean. Are they useful? Total distraction. Are we really living in two cultures of inanimate world and biology? So hopefully I'll leave you with a few questions. So let's start a little bit with the history. And just to remind you of sort of the oldest demon, Laplace's demon. The present state of the system of nature is evidently a consequence of what it was in the preceding moment. And if we conceive of an intelligence which at any given instant comprehends all the relations of the entities of this universe, it could state the respective positions, motions, and general affects of all these entities at any time in the past or future. That's a nice concrete statement of determinism, right? This sort of our sort of creed, right? So the world's deterministic. Moreover, past and future, things are reversible. So why is Laplace talking about this? Well, it turns out this actually is in the preface of his book on the calculus of probabilities. So he's actually kind of set himself up here with a bit of a problem. He just argued that the world is the physical world is deterministic, and he's trying to get you to read his book on probability and chance. Right? So how does he get out of the muddle? But ignorance of the different causes involved in the production of events, as well as their complexity, taken together with the imperfection of analysis, prevents our reaching the same certainty about the vast majority of phenomena. Thus, there are things that are uncertain for us, things more or less probable, and we seek to compensate for the impossibility of knowing them by determining their different degrees of likelihood. So it is that we owe to the weakness of the human mind one of the most delicate and ingenious of mathematical theories, the science of chance or probability. Oh, you bad little humans, you. Your weak little minds. That's why there's randomness in the world. Right? We don't have enough initial data. We don't have sufficiently accurate instruments. We don't have big enough instruments. Didn't get a big enough grant. Somehow, we don't have enough data. Because if we did, then, in fact, the world would not only be completely predictable, it'd be retrodictable. But that's okay. You know, he's sitting around playing cards with his buddies, and he needs a calculus of chance, of partial knowledge. And so things were. Notice the date here, 1776. You know, it's a late 18th century, and we kind of end up in terms of paradigms. How does the world behave? Either it's deterministic, you know, our paradigm is the ideal predictability of a clock. So we have Newton and Leibniz to thank for that way of looking at the world. We write down our differential equations that take an initial state and propagate forward in time, producing a trajectory and orbit in the state space completely deterministically, or we throw up our hands and say, oh, it's random. Various degrees of chance that events are going to happen. There the two shall meet until Poincaré. So just basically a century after Laplace's nice, clean, deterministic statement, we have Henri Poincaré. French mathematician, was actually awarded the prize in the early 1890s for solving a nonlinear problem called the ThreeBody Problem. You have a sun, the Earth, and a massless moon. He worked on the restricted problem, which all three bodies are constrained to move in a two-dimensional plane. And the King of Sweden had offered this prize for this long-standing problem if he could actually solve, well, and actually establish the observational obvious fact that our solar system is stable. So he did that. He went to Stockholm, got his prize, and as the manuscript was going off to the press, part of the prize was to publish the essay, of course, he got a letter back. Excuse me, Professor Poincaré, I'm sorry to bother you, but I've run across a little problem. This is the typesetter. Oh, the typesetters were so good. I'm sure you can fix this, but there's this problem here. You know, please send this back in a few weeks because we're going to production. So Poincaré goes back through this and goes back through this and goes back through this and realizes his proof of the stability of the three-body problem is wrong. Didn't deserve the money, nor the international acclaim. Oh, that when national newspapers would put mathematical discoveries on the front page. Anyway, times have changed. So he repairs to his dacha down on the Côte d'Azur and spends the next umpteen months writing New Methods of Celestial Mechanics, a 1,700-page treatise that analyzes the three-body problem, and he concludes that it is inherently unstable. In fact, I don't really recommend that you read the entire book, but you really should read the last chapter. It's beautiful. He just says, I won't even draw, I paraphrase, I won't even draw for you the complicatedness of the solutions of the three-body problem. Their intricacy exceeds my ability to express to you. And I believe that the complicatedness of the solution set is intrinsic to all mechanical systems of a sufficient complexity. And this is the discovery that even relatively simple, nonlinear mechanical problems can actually actively produce randomness. What he discovered we now call deterministic chaos, and it means that arbitrarily small variations in an initial state will be amplified in finite time, exponentially fast up to macroscopic scale. So he's kind of unburdened us weak little human beings and says the world itself spontaneously produces things that are unpredictable, that appear random. So, but even if it were the case that the natural laws had no longer any secret for us, we could still only know the initial situation approximately. If that enabled us to predict the succeeding situation with the same approximation, that is all we require, and we would say that the phenomenon had been predicted, that it is governed by laws. But it is not always so. It may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have the fortuitous phenomenon. So there we go. The world, even the inanimate world, spontaneously produces things that are complicated and hard to predict. Deterministic chaos, in this sense, leads to this intrinsic randomness. Randomness is intrinsic to the world. Notice, and I'm going to open a can of worms here, there's no appeal to finite resolution or to quantum mechanics or to H-bar. These are just simple mechanical systems. And the consequences are easy to spell out. I mean, you can try to explain this away, but in fact there are a number of different consequences of this. So now I want you to imagine I'm looking at some system. There's a time series. It has 3 variables in red, green, and orange, yellow, coursing over time. I know at least one person in the audience knows where this time series comes from. This is the solution of the Lorenz differential equations for Baynard fluid flow. And I want you to imagine that you, at some point in time, you make a measurement, and you ask how good is that measurement information for predicting sometime t later. And what deterministic chaos tells us is that there are consequences. So, the size of the program you need to predict over that prediction horizon grows exponentially with the time. The accuracy of the numerical arithmetic you have to carry along is exponential in the time. The sample size that you need grows exponentially with the time. And even if you had perfectly accurate arithmetic, the compute time, the number of computational steps, grows exponentially with the time. So this is the sense in which these chaotic systems are unpredictable, surprise, and because over time we are losing information of the initial condition, we need to measure again. Later on, the system appears to have spontaneously generated information that we need to sample again to find out where the system is. So, the sort of standard sort of example of this, and this goes back to Lorenz, the author of those equations, who was a meteorologist in the early 60s studying hydrodynamic flows, and he demonstrated that set of equations to say, oh, notice that this explains how the weather can be unpredictable. It has these built-in instabilities, exponential instabilities. And indeed, weather's complicated. It's hard to predict. Look at these flows, nice little kind of almost like a vortex, and the cloud structure there, evaporating away. Weather's unpredictable. No, weather's predictable. So, what's the weather outside? It's a sunny, nice day. Okay, what's the weather going to be in 30 seconds? Sunny, nice day. Well, actually, I think I saw some clouds. What about in 2 hours? Well, then you probably would think back, oh, actually when I was walking, did I look at the horizon to see what was coming over the ridge? How about predicting the week? 2 months. So what you see here, when you think about it, is these systems that are unpredictable, there's sort of a contour of increasing unpredictability. And that's actually what we're interested in. Not that it's unpredictable or predictable, but in fact the way we lose information has a particular shape to it, and it's informative. So systems on short periods of time can be quite predictable, like the weather. Whereas over different time scales, we see that, in fact, we lose that ability. And how that comes about, that shape, tells us a lot about how the system is generating its information, how it's structured. And that's what I want to talk about. A little kind of historical aside, there's this nice article by Heisenberg in Physics Today, 67, and he's talking about nonlinear problems. There's this kind of interesting speculation here that maybe even Schrodinger's equation will be replaced by some nonlinear fuller description. Well, actually what he's talking about here is illustrated above. Namely, he argues in this article that one of the burning questions of physics in 1967 was fluid turbulence. Well, there's some history behind that statement of his. It turns out that Heisenberg's PhD thesis was not on quantum mechanics. It was on fluid turbulence. Why? Well, Sommerfeld said, trying to defend him, this young Turk mathematician type, his colleague Weil said he's no experimentalist, and back in the 1920s and 10s, physics was mostly experimental. And so he wanted Heisenberg to work on a practical problem like turbulence. The problem is, when he came around to defend his thesis, Weil and Sommerfeld and others on the board actually gave him a mixed pass. Sommerfeld gave him flying colors, and Weil failed him. He was so embarrassed, he skipped the celebration dinner party and went right up to Max Born, who'd just given him a job, begging for the position. He was so embarrassed by his failure. So that's just a kind of a little aside. Maybe there's a lesson for some of us about persistence. So at the time, fluid turbulence, the main theory of why fluid flows get complicated, this is flow past the cylinder here, is due to Landau and Lifshitz, namely that the flow consisted of a large number of simple harmonic oscillators tuned to different amplitudes and frequencies. In other words, if you would take a power spectrum from that, you'd see many, 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 many peaks. Well, it turned out that this sort of interested folks in the 60s and 70s after Lorenz's work, and people started studying more assiduously different kinds of flows. The picture up here is something called Couette Flow, and it is a fluid layer between two concentric cylinders with the inner cylinder rotated, and one studies the different flow configurations as you vary the inner cylinder angular velocity, and what you see are different. Well, basically what's going on, you're sort of convecting angular momentum from the inner cylinder to the outer, and you get these convective cells. So this is a favorite flow. And the idea was, in fact, that we could determine whether the Landau picture was correct or not. So this is due to Lorenz, I mentioned, but David Whewell and Floris Tawkins, two French mathematicians, they came up with this hypothesis that there's a low-dimensional chaotic system, a la Poincaré, describing this. Well, it took about a decade, I guess, from 72 to us finally showing that by looking at measurements of the Couette flow, you can reconstruct an effective state space and show that the solution set was one of these chaotic attractors with a positive entropy rate and Lyapunov exponent and so on, which give a measure of that degree of instability. So these systems actually, in the world, fluid turbulence, one example, are described by these chaotic systems that are inherently, actively producing randomness, actively hard to predict. Well, so how are we going to think about this and be quantitative? So it turns out the appeal was made to the theory of communication introduced by Claude Shannon in his 1948 paper, Mathematical Theory of Communication, although he was working at Bell Labs at the time, a communication company, and he was mostly interested, not in turbulent fluids, maybe noisy transmission channels, but how to transmit information. At that time, that meant human speaking over noisy electronic equipment such that the receiver could actually understand what you were saying. But this instigated this interest in and quantitative measure of degree of surprise or information that we've adapted to describe turbulent flows. But what is information? Well, my favorite definition is actually due to Gregory Bateson, the sort of anthropologist, sociologist, husband of Margaret Mead. He was a member of this interesting crew of people, von Neumann, Shannon, Margaret Mead, Norbert Wiener, all meeting in the 1940s and 50s, and they're all fascinated by what this information and communication theory could mean. Gregory Bateson defined information as a difference that makes a difference. So it encapsulates Shannon's notion of surprise, I need to measure the system again, but also throws in this aspect that it's something that's relevant or important to an observer. The story is maybe a little apocryphal, is that when Shannon was talking to John von Neumann about his new theory of information communication, von Neumann told him to call the function he was using entropy. Why? Well, von Neumann is said to have joked, then no one will ever know what you're talking about. So, back to Poincaré's demon, this inherent deterministic chaos. It was actually the Soviet mathematician Kolmogorov in the decade after Shannon adapted Shannon's notion of information theory in discrete systems to continuous physical systems. These days we hear a lot, at least in my world, about information and entropy in physical systems. But in fact, there are some important mathematical moves you have to make to show that Shannon's notion is actually appropriate to physical systems. And that was done by Kolmogorov. So he and his student Yasha Sinai introduced this notion we now call the chaos entropy, or it's really the Shannon entropy rate when you look at a physical system as if it's a source of information. And it's measured in sort of bits of surprise per unit time. And now we have this way of talking about how a nonlinear dynamical system or a turbulent fluid is actively producing information, some number of bits per second. We can talk about how one system is more random than another, more unpredictable than another. And so we have this way of measuring randomness, degrees of randomness. So what about physics? So this is actually kind of my main point. This is a lot of historical aside, but I want to talk about information more directly in physical systems, in particular in thermodynamic systems. Is there a physics of information? Well, I guess we've been living in the information age for a while now. I guess we're in the age of iPads or something, I don't know. Information age, right? We're deluged by this. In fact, every year it seems to get even more outrageous. But the information age. It's interesting to think back to the time of Maxwell and Clausius and the Industrial Revolution, where it took quite some time for the proper theoretical description of heat engines to evolve. But when they did, it was extremely powerful that we finally could understand and design and understand the constraints that limited the efficiency of heat engines. This drove, that was a period of human development that we wouldn't be here without it, right? Everything is this huge social transformation. Before that time, basically everything that humans had to be built by human hands, right? The Industrial Revolution led to us harnessing individually vast amounts of energy. Look at this room. So my puzzle is, here we are in the information age. What's the analogous thermodynamics? Shouldn't we have something? That's the theoretical foundation of the age we're in. I mean, look at the power that it gave us, you know, in close alliance with engineering and invention and even the creation of the patent system in England. But the whole industrial revolution gave us these powerful tools. Isn't it about time we developed some theoretical foundation for thinking about the information age? Right? And I'm not just talking about measuring, you know, terabytes. I want to know what the physics of this is. We design these devices for our purposes, but they're physical devices. So we have things we can make that embody both being physical and being information processors. So what's the relationship between the rate of information processing and the physical properties? And we all know, hop on the plane, after a while, put your laptop on your lap, you start running Excel, your lap heats up. So there's obviously some kind of thermodynamic consequence of doing information processing. But what is that? Is there any fundamental physics in this? Or is information just totally separate? I mean, I know some people have run across discussions of information theory before, and a lot of what you hear is, oh, that's just subjective. Depends on the observer. Okay, if that's what you think, then there's no objective physics of information. So a number of people have been thinking about this, in particular, what are the physical limits to computation? So I wanted to kind of be a little more historical here before I get to some of the technical work. This is the physics of computation meeting at MIT in summer of 1981. And there are a number of curious folks here. For example, Dick Fineman, John Wheeler, Freeman Dyson, Rolf Landauer, who will play a role in what I'm going to discuss. He's probably the first to really articulate the problem of physical limits to computing very clearly. Also, Greg Chaitin played a role. He's actually a child prodigy, is actually competing against the Soviet mathematician Kolmogorov and their theory of information and randomness. Well, okay. It's my more hirsute period. I think I'm still wearing the same jeans, though. Oh, and then Charlie Bennett, who will also play a role. It turns out that Charlie, it's been decades now, he's the one who always takes the group photo. He's passionate about this. In fact, this particular photo, I thought I had lost it. But last summer, I met Charlie and said, you know that workshop we were at? Do you know anyone who has got the picture? Open up his laptop and email it to me. Anyway, so Charlie and Rolf Landauer played a big role. This was the conference at which Feynman proposed that we build quantum computers. Of course, he was a physicist. He didn't want to run Excel. He wanted to do physics, right? So there was a lot of discussion, argument about this. I kind of got in an argument with Feynman over this particular issue. But I want to just point out one modest little thing. That in the proceedings, the immediately preceding paper is by these pair of guys, Crutchfield and Packard. So this notion of the physical world storing and processing information, Feynman's introducing, let's think about the quantum setting of this, which some people already started to do in terms of quantum dynamics, but he of course was saying, let's make a programmable quantum machine. But this whole notion of physics of computation, fundamental physical limits of computing go back a number of decades. And there's been this kind of motley little crew sort of interested in these issues. But now, things have changed. In particular, we know that the more scaling laws and all the sort of economic system we've built on exponential improvement, increasing density of transistors on a chip and so on, that's been over for 10 years, right? So now we're building these massively parallel machines is kind of obvious. I don't know what else to do. Let's just build a lot of them. So here, just to kind of put a number or two on it, we're looking at the power dissipation per logical operation as a function of time. This is from my colleague Mike Rukas at Caltech, because we're very interested in these fundamental physical limits and where we're going. When are we going to bump into these physical limits? So this is showing you, mostly in CMOS technology, where we are today and where we are in terms of, actually, Rolf Landauer's prediction. That's the purple curve there. The claim which we'll talk about, is that there's an irreducible amount of energy dissipation for doing elementary information processing operations. So he introduced this notion in 1961 that logically irreversible computing, and what he means there is if I have a circuit that processes some information, if I cannot infer the inputs from the output, it's logically irreversible. Think of an AND gate, X and Y. From the output Z, you can't determine what the input was. And then according to him, because the circuit is a physical device, when it goes through this logical irreversible step, it's constraining the state space. And by Liouville's theorem, state space is conserved. Therefore, where does the constrained state space go? The reservoir state space has to grow. And that's a little puff of entropy into the reservoir. So that's what's behind this bound here, that you have to, there's this smallest amount of heat that you have to invest to do, in this case, erase a bit. One simple operation. Okay, so we're kind of jumping forward and now jumping back to Maxwell. So now what I want to do is try to tie in more directly to this thread about unpredictability and randomness, information being produced by physical systems. I want to kind of reground this in physics, and we'll talk about Maxwell. So this is certainly a hackneyed example here, right? So, right, somehow the second law lets us say that it's obvious that the reverse process can't happen. Right? Right? Second law forbids this. And why? So here's one view that we can attribute to Maxwell. And I know I'm covering things that are very familiar to people, but we're going to need some of this in a little bit. So Maxwell's demons is looking at a box of gas molecules that has a partition, and he can control a trap door. He or she, I don't know which demons are what, I don't know. Such that by observing the fast and slow molecules, he can preferentially open the doors so that all the cold molecules end up on one side, all the hot ones on another. The resulting temperature difference means that he can operate a heat engine to produce useful work. So this is tantamount to saying his ability to observe and control and make decisions, being intelligent, allowed him to violate the second law, right? So that's supposed to be, at least in his time, not possible, ridiculous. However, times have changed, right? The possibility of somehow using intelligence through observation and control manipulation, leads to this heat difference and a violation of the second law. But I don't know, these days, such a demon that had that much control and observation ability, I don't know, maybe it's possible. Or maybe we're just kind of fascinated with our current technological fantasies. But maybe it's possible to reassemble the glass. So that's what's puzzling me right now. Something that we've taken for a very long time. We've gotten rid of perpetuum mobile, the first and second kinds. We're used to all this stuff. But now we're building systems on the nanoscale. So for small scale systems, we know the second law doesn't apply strictly, right? The second law is a law about large scale systems, or it's a statistical law. And what about fluctuations? Can we build nanoscale systems that, in some sense, are smart enough, like a demon, to take advantage of favorable fluctuations? And I'll give up asymptotopia to do. Maybe if it just did it transiently, this would be good enough. So I want to talk about this possibility. So probably the most cogent analysis of Maxwell's demon was due to Leo Szilard. Some of us know him as the patenter and inventor of the atomic bomb. But he had this interesting paper in 1929 on the decrease of entropy in the thermodynamic system by the intervention of intelligent beings. There's that word again. Intelligence? What is this? However, what he did was a good move. He says, wait, Maxwell, stop. You didn't give the demon a physical instantiation. Let's do that and reanalyze the system as a joint system. So kind of one of the key kind of lines in the papers, we must conclude that the intervention which establishes the coupling between Y and X, demon and system, the measurement of the system by the observer must be accompanied by a production of entropy. So he argues that the demon doesn't get to do this stuff for free. And lo and behold, when you go back with this simple observation, putting the thermodynamic system and the demon on a physical footing, lo and behold, second law comes out just fine. So here's a cartoon picture of how his little demon worked. Very, very simple. So we start with a box, the canonical box of gas molecule. And then what the demon does, it slides in. There are all sorts of little tricks that this last 150 years of Maxwell's demon, all this cleverness. So one of the cleverness, putting in a partition with no energy gap. But let's go with the argument for now. We can talk about it afterwards. So the demon puts in this partition. So the demon has a little internal state, A or B, and then the demon observes what side of the partition the particle is on, and then if the particle is on the left side, the demon allows this partition, movable, to move out, picking up P dV amount of energy, or in the opposite case, it measured that the particle was on the right side and allows the partition to move this way, extracting energy from this randomly bouncing molecule. The demon removes the barrier and then lets the molecule float around. The device resets. Right? This is a cycle. It's an engine. It's a cycle going repeatedly. And by doing this, you can temporarily extract energy, but then that gets lost when you rethermalize back to the reset state. And this is what Charlie Bennett and Rolf Landauer sort of emphasized in their energy cost of erasure, that resetting the system to a canonical state costs energy irretrievably. I will shortly take issue with this, but okay, that's a simple enough cartoon. You can actually imagine building a real mathematical model of it. So going back to Szilard, and you just read between the lines, and you just implement this thing. So what I'm going to do is just quickly describe 3 different transformations. The most important thing to realize is that when we do this kind of accounting, both the daemon or control system and the physical system you're controlling live as a joint system. We have to look at the joint state space. And so that's all I've done here. The molecule can move left or right, and the daemon, we are also going to keep track of its memory, also with just a particle. So what I'm going to show you here are a series of transformations of what it means in the joint state space for the daemon to measure. Well, the daemon measures what that means. It means the daemon's memory macro state, call it, B, gets correlated with the particle being on the left, or memory macro state A with the molecule being on the right. So it's like a little identity map. Looks like a block diagonal matrix almost. What does it mean to extract energy? Well, if the particle's on the left side, the partition moves this way. And if the particle's on the right side, I let the partition move this way. So now the location of the particle is diffused horizontally. And then we need to reset. So I take this now and squish it back down to the original size it was, and then reset and start over again, so it's a cycle. The colors here are just to help guide the eye. Just tells you that the particle started green particle on the left, yellow particle on the right. Okay, but this is a process. We do this repeatedly. It's actually a series of 3 piecewise linear mappings in the parlance of dynamical systems. We measure, we control, we extract energy, and then we erase and we start over again. So some of you learned a little bit about nonlinear dynamics will know this is something called the Baker's map. And you can write down, I won't go through this obviously, exactly what those transformations are step by step by step. And they get repeatedly applied. And it's showing the Szilard engine as a cycle. The composition is this Baker's map. And it's well known that it's a chaotic dynamical system in the sense of Poincaré. So let's see if I can. let me do it here. No, I'll do it over here. Let's see. Okay, measure. Okay, left or right. Now I let the partitions move. Okay, extracted my PDV energy, and then I reset. Okay. Well, it's an engine. It keeps doing this again and again and again. And this is where the colors are kind of handy. Remember, molecule on the right was red, molecule on the left was blue. And what you see, and this is, again, if you're familiar with the Baker's map, this phyllodoe construction of the distribution of where the particle could be. So we have the stretching horizontally, and that's corresponding. That is actually why the system is exponentially unstable. And then we're compressing back down, and that's causing these little phyllodoes. The layers like this. And it goes off down to infinity. Well, the nice thing, what I like about this model, is that this is something you can do on the back of several envelopes. In fact, at this point, I have 2 undergrad senior theses that will work this through. It's that straightforward. But there are all these questions we can answer. So in particular, let's go back to Landauer's analysis. One thing you can do is you can calculate. You might have noticed I had a parameter in the model that said where the partition goes in. That was delta. And then there was another parameter, gamma, that was the distinction between the daemon's memory macro states. Well, we can vary those things around. See what happens. They're different mappings. So we can calculate the dissipated heat for erasing information. The blue is for measurement, when the daemon degrees capture the molecule's location, or during the control step, the expansion step. And lo and behold, we recover KT log 2 for the Bennett erasure. Measurement is free, 0, but then it's KT log 2 for erasure. But you can see the curves cross over each other. So there's actually an anti-Landauer principle where erasure is free, erasing information is free, and the measurement costs. Well, and so on across the curve. So the kind of improvement here over the Rolf Landauer, Charlie Bennett, only erasure costs you. We have some design flexibility in how we build our implementations now. It's really, what's important is the net change in the joint system's state space. You have to track the sort of microstate volume change. That's what's going to cost you. Well, how do these daemons work? I mean, one question is, okay, this is a nice idealized thing, but someone comes up to you and says, oh, this motor protein crawling across this microtubule, it's actually doing work. How does it do it in this very stochastic environment? You'd like to have some tools that would let you see how much energy is being extracted from the heat bath, how much work is being done. So I want to talk very quickly, and this is maybe the most technical part of the talk, just to kind of hint at some of the rules, but we all do this. I have to tell you a little bit of the technical stuff. Okay, so the question is how I'm looking at my Szilard engine here, and I want to figure out what information it's storing, what information it's creating. So the way we do this is to look at the process of the daemon and the molecule, AB, left, right, AB, AB, whatever, that's the symbol sequence. And what we do is we group together all of the pasts that lead to the same view of the future. So that's what that top equivalence relation is about. So we'd say 2 different pasts, left arrows, are the same. We put them into the same bin when the futures from those different pasts lead to the same prediction of the future. So we're going from an uninterpreted time series, just behavior. Think of this as just this bi-infinite chain of random variables. And at each moment of time, I'm stopping, taking into account the particular past that I saw, and I use that to do the best prediction I can of the future. So this notion of the effective states of the process, it's that set of times, particular pasts, that all lead to the same future distribution. So we call these causal states. It's a way of reconstructing things. Actually, in a sense, how we went from that Couette turbulent flow to showing those strange attractors. But this is kind of a discretized version of that. The nice thing about this is you can show that the resulting set of states in their transition dynamic, here I'm giving you a probabilistic state machine picture, need not be finite state. Fractal continuum states and so on, is that this representation, the epsilon machine, you can show it's an optimal predictor. No one else can do better than you if you have this in hand. It's also of minimal size. And anybody that comes up and says, oh, I've got a predictor just as good as yours and it's small, they're equivalent. So it's a unique. In some sense, it's the ideal representation of the internal information processing of the system you're looking at. And we can calculate various things. Probably the most important one is not so much the Kolmogorov-Sinai entropy rate, which is just the state, causal state average branching uncertainty, unpredictability in the next symbol, but actually the amount of Shannon information that's stored in the causal states. So this is kind of asking the question, how much memory does a physical process have of its past? Simple question. So not only how random it is, h mu, but also how much memory does it have. And these are complementary coordinates. Shannon would tell you, oh, all I care about is the information production rate. And now we're able to actually look inside and look at the mechanism and see how sophisticated the mechanism is in terms of how much memory it's stored. So it's a useful tool. Imagine you had your favorite, 2D Ising spin model and a temperature control. So what you do is you set your temperature and you measure the amount of per spin entropy, and then you also calculate this stored information. And what you see is at the extremes of completely predictable and completely unpredictable, low and high temperature, the systems are statistically simple. There's only one state. If you were looking at a fair coin, by definition kind of memoryless process, every history leads to the same view of the future. Everything can occur at every moment in time. The system stores no history. That's what falls out of that equivalence relation. Or if it was all ones, then the future looks like all ones. You only have a single state. So that's why the structural complexity measure is 0. And all the interesting stuff happens in the intermediate range. Systems with more memory, they pick up more correlation, they store more information of their past. And so we have this notion now of intrinsic computation. At least in theory, I can look at any system, waterfall, my roughly idling car engine, and ask how much historical information does the process store? In what architecture is it stored? What are the causal states, transition structure? And then how is that stored information used to produce future behavior? These three basic questions. So, right? Stored information, C mu. What's the architecture? Well, it's actually the set of states in their transition, and then how does it produce future behavior? That's related to information production. And we can say, nice little things using these things. We can talk now about a system being unpredictable, has positive entropy rate. We say a system is complex or structurally complex when the memory, C mu, is positive. We can talk about this very vague notion, it's very popular sometimes, that systems over time actually become more structured. So we can talk about this statistical complexity, the amount of memory that's being stored increasing over time as a quantitative measure of the degree of emergence, or at least temporal change in structural properties. And another interesting thing comes out of this. There can be this interesting connection to cryptography, this difference between the internal state information, historical stored information, and the amount of information, which I've labeled here E, that is observed, the amount of correlational information you get just from observations. So what happens in this case when the crypticity is positive, it's that the internal state information is actually hidden from you, but spread out over long times. It's still discoverable. You can still get the causal states and reconstruct the model, but in fact, it's sort of hidden from you. There are ways of hiding information. It's interesting parallel with, it's like scientific discovery is cryptography in a way. Getting back to the Szilard engine, you can go through and observe the AB left-right time series and reconstruct this state machine for the Szilard engine. And you see that it has an entropy rate that depends on where I put the molecular partition divider, delta, that position, and then the amount of memory it stores is log of 3 plus that. Well, log of 3 because it's period 3. Measure, control, erase, measure, control, erase, measure, control, erase. So, and this is the minimal description of what's going on, the information processing that's going on in the joint system. So the summary of this is it's actually a strategy for analysis. I'm not talking about a particular domain of physics. I think this should be applied broadly. So the idea is that an information engine is this dynamic over a joint state space between the physically embedded controller and the system that's being controlled. You want to look at the joint state space. The causal states, you apply that equivalence relation to calculate those things. And it gives this, from those particular equivalence classes, it captures all the information processing and emergent organization. It's kind of a zeroth order measure of intelligence. You can take the amount of memory. So at least now we're making a little more concrete this vague word showing up on our historical literature. At least tell me how much memory the system has. Okay, you can show that these the Lyapunov exponents measure the amount of dissipation that the engine's putting into the reservoir, and maybe kind of a nice take-home message is that the engine's efficiency, the amount of energy, disorganized energy that's converted to useful work, is given by the degree of chaos, the Kolmogorov-Sinai entropy, its information production rate. So this is one of the first connections between dynamical systems, physics of nonlinear systems, and thermodynamics. Our engines have to be chaotic. They have to have instabilities built into them, otherwise they couldn't be extracting useful work from the heat source. Actually, when I say it that way, it's almost kind of obvious, but I like it because I've been working on chaos for 30 years, and finally there's a use for chaos. It runs my engines. Okay, so I think I'm going on a bit long. I can kind of tell. How are we doing on time? 5 minutes? Oh, really? I'm on time? 7 minutes to go. 7 minutes. Oh, boy. Okay, so Szalard's point was that his more detailed analysis of the Maxwell demon, when he made the nice move of making, observation and control of that little portal in the partition, giving that a physical instantiation, in particular, memorizing which side the molecule was on in the partition, that was all consistent. In other words, the Szalard engine, it's consistent with the second law. Doesn't that so interesting? We want things, to build things that have a net thermodynamic benefit, not just be consistent with the second law. So let me quickly describe, in the last few minutes, about these information ratchets. And also help me make a little closer connection to maybe some of the way people think about modern computing. So what we have now is some thermal system. Think of a kind of detailed balanced stochastic dynamic as the ratchet. It's connected to a thermal reservoir. Everything is at temperature T. And then there's some cartoon picture of a work reservoir, something where I can either take energy from it by lowering the mass or put energy into it by raising the mass. Okay? And that's all controlled by this ratchet, the gray disk. But what is driving this now is an information reservoir. This is kind of this new thing. An information reservoir. I mean, what are reservoirs? What's a heat reservoir? Well, it's an idealization. Nothing is a heat reservoir, but the idealization is that if I give it energy, it has to take it. If I want energy, it has to give it to me. Right? What's a work reservoir? Same kind of thing. So an information reservoir, we can read information from it, but it doesn't change its entropy. That's the idealization. So I'd say in some sense now we're kind of appreciating that modern non-equilibrium thermodynamics is really just a calculus of different kinds of reservoir. Because it's always been that way, but it's one way to think about this. So what I'm going to do is measure the amount of information coming in on this tape using the entropy rate of the input. And then there'll be an exhaust part of the tape here. So this ratchet starts moving along. Every time it reads a new symbol, that actually biases its internal stochastic dynamic, which is sitting in this heat bath, equilibrates for a bit, writes something to the output, the blue part, and then moves forward and grabs another bit. So what can you do with this? Well, the interesting thing is you can start thinking about computing in a new way. So this is actually just a stochastic version of this canonical model in theoretical computer science called the Turing machine, finite state device that reads and writes on a tape. So I'm just adding a little bit of stochasticity to this and worrying about a thermal substrate. So there's some interesting things you can conclude more generally about thermodynamic constraints on computing in this more generalized setting. So the first thing you can write down is a rather big generalization of Landauer's principle of the cost of erasing a bit. You can look at the amount of work, you can bound the amount of work by the difference in the randomness or the entropy rates of the input and output tapes. So, I mean, just to think about Landauer's principle, well, I'm erasing a bit, so I start off with one bit of information, and I force it to be in one state, so the result is certain. So I go from one bit on the input to one bit on the output, and take your minus signs, and you can show that there's this middle amount of heat that's devolved when you do that. But this is much more general. We're now looking at the rate of change of these entropy rates of the input and output tapes. Think of those as programs. And one of the conclusions you draw is that ordered inputs are really a thermodynamic resource. I can turn this into an engine when I'm producing work by putting the right kind of information, correlated information on the tape. In other words, information is a kind of fuel here. Actually lets you do positive constructive things. And then information processing second law is useful because then you can go through and just look at, oh, I'm generating positive work and I'm increasing the randomness on the output, I'm exhausting randomness on the output. Well, that increase in randomness allows me to convert the disorganized thermal work into useful work. That's an engine. Or I can turn it around and have something that takes work, lowers the mass, and uses that to erase random bits on the input tape. So we have an eraser, generalized Landauer erasure. And of course, you kind of look on particular models. The P and Q here are parameters in that stochastic dynamic. I didn't show you what the detailed balanced dynamic was, but you can go through the space of parameters for these little engines and figure out what range it's an engine, what range it's an eraser. So the important thing is that sort of illustrates that this entropy rate, as opposed to just looking at the statistical bias, is important. Previous proposals for these information engines just, in a sense, converted statistical bias on the input for a compensating change in the thermal reservoir and allowed that energy to be turned into useful work. Here, we actually discovered a new kind of engine that operates on pure correlations. So think about the two extremes here. A random binary string coming in, right? The statistical bias is 50-50 for zeros and ones. So is 1 0 1 0 1 0 1 0. Those are kind of different sequences. In particular, 1 0 1 0 1 0 is boring. Its entropy rate is 0. It has a big thermodynamic effect, and that's what we're kind of outlining here of the PQ space. There's a whole new way of doing erasure that has to do with correlated inputs. So having something like this information processing second law actually let us discover new kinds of information engine design. Right, okay, so that was a whole lot of history, and I guess maybe it seems like philosophy. So to kind of finish things off in minus 1 minute, I will talk very briefly about some experiments we're doing to test these ideas down at Caltech at the Kavli Nanoscience Institute. Mike Rukas, my buddy, is the PI down there, and we have a great set of students. So we're looking at two platforms. Let me just describe one. So right now, Mike Rukas is sort of a master at building these NEMS, nano-electromechanical systems. These are, and it kind of warms my heart as the analog guy, little analog computers on the mechanical analog computers on the nanoscale. So we make these little bars. If you put some tension, the bar in the middle will bend. It'll have two different rest states. And that result is you have a double well potential. I can store and process information with a double well potential. So that's what we're building down there. The hard thing, this is, the naive theorist at making an admission. The hard thing is measuring heat. Who would have thought? So we're building a calorimeter, kind of off-board calorimeter that's connected through superconducting wires to the NEMS device. And the point is the information processing second law, there's a physics side, which is about work and heat, and there's an information processing side, the difference in the entropy rates, or Landauer. There are two sides. You have to simultaneously measure both to actually test this idea, and it hasn't been done yet, despite things that have showed up in nature and science. Independent measurements of the information processing, and you need to know the dynamical state and track it in some detail, and to do the calorimetry, actually measure the heat flow, the flow of entropy into a reservoir, calorimeter. So that's what we're up to. Recent devices, oh boy, it's starting to work. And then, turns out if you take two double well potentials, you can couple them together in a way such that you can implement that Szilard engine. So this is what we're trying to build down there. Hopefully this will be online in maybe 6 months or so. What I'm showing you here is at the very top what the potential is. So each double well potential is fourth order, second order, and there's a tilt parameter. And then there's just at the very end a linear coupling between them, or bilinear coupling between them. And that's all you need. And then with these coefficients changing over time, you can actually implement a fuzzy version of that cartoon I gave you, that animation, to actually do a Szilard engine. So, and we'll be able to look at when the heat gets sucked in, the heat gets put out, and so on. Measure this directly. So I will stop there. I was going to make some silly comments about Darwin. I'll just leave it alone. My own feeling about some of these ideas is I'm hoping, actually, the largest well, it's not only rethinking what nonlinear thermodynamics is and information processing and giving us maybe a more a physical view of the information age we're in and what these devices are doing for us and could do better. But I also think it's a new picture on how biological processes operate, what their thermodynamics is. So I'll just put up the summary here. So I started talking about randomness, but that was a complete ruse, right? Unpredictability. Shannon's notion of incompressibility and surprise. Really, the message I was trying to pitch here is that structure and correlation are extremely important. My koan for this is how nature is structured is how nature computes. And this kind of, to understand that, you kind of have to loosen up two things. You need to loosen up what you think computing is, right? Our current notions of computing are so socially determined by these things. You know, we're in this current digital era. But, well, I knew some of the old guys, Dave Huffman and other folks. In the early ages of information theory, they thought the whole world was storing and processing information. So I'm kind of coming back to that. Kudos to them. Yeah, deterministic chaos actually drives. That's important for heat engine functioning. You need instability to have a thermodynamic heat engine work. Intelligence, there's a start. Memory, organization of the states, how many states you have is some kind of proxy for that. And then this new second law extended to deal with information processing. And the very recent thing is what we're calling modularity dissipation. I think this is the first time that the architecture of a physical or biological system has been shown to actually have thermodynamic costs. We all build the computers here modularly. Why? Weakness of the human mind, because it's easier to think about. But maybe, I want to build an adder. Why organize in this modular fashion all those atoms? Maybe there's a more efficient way you could compact it down. You can show that that would actually be the most thermodynamically efficient. This kind of minimal structure. Every time you break a system into modular components, it's actually costing you. But maybe there's a positive. Maybe evolution actually took some advantage. It'd be interesting. I have two eyes, so that's kind of modular. So maybe there's some very interesting consequences of thinking about the thermodynamic cost of modularity in a biological setting. Well, you've been very patient. Thanks so much.
Great. I guess we can take a couple of questions. Yes?
So I have an immediate question about Landauer. Without belaboring it, what you've been describing is a set of physical phenomena, rather difficult to describe, but you know they're there, that require dumping an instability to dump entropy when you make a decision, because that's what a decision is. Now, I think there are people around, and I don't work in this field, who claim that the Landauer limit isn't right.
Yes.
So would you like to take a stand on that?
Well, the cheap, but...
For money?
Oh, that's entirely different now. So let's talk. Well, it may be involved. So you might be thinking of Luca Grammatoni, whom I know well. He's come up with some dissipationless logical gates. And it's a very nice talk, kind of against this Landauer-Bennett erasure. The perfectly honest answer is that it's quite controversial right now. So my own view is that he is not being entirely fair in his model with all of the physical and energy accounting. But then you get down to, at some point, kind of defining terms. So me? Let's do the experiment.
Okay.
So I'm not going to give you a definite answer. I appreciate...
I really wanted to make some money, but you're not going to do it.
Oh, that's what it was, making money.
Excuse me, I want to vote for Landauer. So my money's on
Okay,
Landauer.
okay.
I have good odds.
Yeah, pretty good. Yeah, modified, more flexibility, not just erasure. Then we can agree.
yeah.
Okay, good. Yeah. No, it's interesting. It's a wonderful time. I think there's some just very basic issues people are debating right now, and so it's a very exciting time, especially with new
With this
nanotechnology.
NEMS device you talked about at the end, how well can you distinguish interactions that add or take out heat versus doing a little bit of work on the device?
Yeah. So that's, yes. That makes the experiment quite hard. I'll just mention a few things and give you some sense. So to isolate sources, extraneous sources of heat and work, we're running everything down at 4 millikelvin. In particular, most of that's driven by the design of the calorimeter. So we have to modeling in detail how the logical device, the NEMS device, couples through electron-electron-electron phonon interactions and how that flows down into the calorimeter. And we're measuring all those degrees of freedom exactly, because we have to make sure the calorimeter actually has to have these fluted horns, because the whole thing is suspended above the actual substrate that damps down the phonon dispersion, and takes a lot of detailed design to make sure you're getting it right. So the target resolution is, for the calorimeter, is 10 to the minus 24 joules. I don't know, you remember that CMOS plot I had? That's another 2 decades down below, and that's what we feel like we need for fine resolution in order that all other fluctuations into account, we'll be able to make some statement about the Landauer principle. And those will be some of the most accurate temperature measurements ever made. In fact, I say that, and people in astronomy start talking to me. Really? You can do that? So we'll see. Yeah, but that's yeah. So no, you have to isolate all these things. In fact, if you remember the Fermi-Pasta-Ulam problem back in the 50s, right? Fermi and Pasta-Ulam. They had these new digital computers at Los Alamos, and they're going, hey, what about this thermalization problem? Let's take our Einstein crystal and put in just a little anharmonicity into the mass atom-to-atom coupling. That should thermalize everything. They ran it, and sure enough, put in kind of macroscopic energy, one mode, gets all disorganized, spectra's all excited, keep cranking, and then it all reassembled. There was a recurrence time, which is actually what Poincaré's complaint to Boltzmann was. But anyway, so we're actually having to worry about that in our calorimeter because we have so few degrees of freedom. You need the mass to be small so that you actually have some time resolution, so that when the heat comes in, it actually has an effect over some period of time. Can't make it big, right? But then that means you have so few degrees of freedom, you actually have to worry about the dynamics of the constituents. So stay tuned. Looking forward. Yeah.
What temperature range are you actually going to be looking at?
Oh, this?
Yes.
Yeah, 4 millikelvin is the target. Yeah.
And what happens if you get it down well below 4
Or
I don't know. That's Michael Ruckus's thing. He loves, he can't, next year we're going to cool it all down. Okay, I should mention there's another system we're looking at, which is a flux qubit. Right now we're running it in kind of the classical mode. We're just looking at the double, well, actually the washboard potential from the Josephson. The potential, it's like a pendulum type. And that we're planning to move into the quantum regime to study quantum engines. So, yeah. We're not making quantum computers. We're trying to understand their thermodynamics, which oddly, these companies don't seem to care about. But okay, I'm not saying anything.
Okay, great. Well, let's thank the speaker one more time.
Thanks.